Hello, everyone, and welcome to Handmade Hero, show where we code a complete game live on stream. We are going to be continuing our lighting work today. We actually were told specifically in the so we left on the thing where we gotta all right, we gotta debug the lighting. I cleaned up sort of the path that the lighting goes through, so that we weren't doing as much unnecessary work. But I didn't actually have a chance to debug any of it. Or really finish it up. So that's what we were going to be doing this weekend. We had some bugs in there, well, at least one bug in there, and although we would have tried to find that today, actually on the Handmade Hero GitHub, which I guess I'm not logged into right now, but I probably should have done that, we actually had someone, Scriver wrote in over the week saying, hey, by the way, I found the bug already in the lighting, and I fixed it. And so I'm actually tipped off to what the bug was, so I can't actually do the work of finding it today, or at least not that bug, because we've already we know what it is now. So let me just show you what the problem was when we did some of the work of moving to the, when we sort of said, all right, let's streamline this, so we're gonna actually do everything directly in the Voxel, and we're gonna do a SIMD version of the update and all that stuff. When we were computing the weights, I think one of the things, and I'm not sure I can make it happen here because you can't really see it very well, but one of the things we noticed is that there were parts of the lighting that seemed like they were always black unnecessarily, like they were supposed to not be, but they were. And it turns out that the reason for that, at least assuming the bug report was correct, I never look at the code unless we're on stream, so I didn't go verify it. But if you remember, we create sort of this diffuse weight map concept here, and we put a bunch of information into it that we're going to use to look up to do multiplies later. And what we've got is just an off by one bug in there where we're putting in the wrong information. I should say, sorry, we're putting the information into the slot wrong because one of our lookups is wrong. And that's kind of makes sense because we haven't polished this code. We haven't gone through and actually cleaned up how everything's being looked. We got weird constants like this -2 and all that stuff in there. We probably want to get rid of. But so let me just show you where it is. If we go to, I think it's, what is it called? Build diffuse light maps. That's the one. So if we look in here and we look at how these things are being updated, right? And then we go to the code that actually uses them, which is down in the, nope. Where is it? Here it is, I think. No, oh, sorry, right. We're doing these multi-threaded now. So it's actually in the compute like computation call. Yeah, we've gotten pretty fancy, haven't we? So here's that work computation that's actually being done. So it's actually out here. And if we look at where this is being done, so I believe this is it right here, right? And we've got our pulling the map out. So you can see here, when we get the weights, there's a ty -1 being done here and a tx -1 being done here. And then when we look it up, we've got a ty and a tx -4 being done here. So you can see that we're actually looking this up differently because this is the same loop in the outside, right? You can see that these are meant to line up. But this one's looking it up with ty, and this one's looking it up with ty -1. So everything was shifted by a row, which leads to lighting that sort of looks sort of correct, but is off a little bit, right? It's rotated in our octahedron a little bit, and then just one of the rows eventually will get to garbage. And that's the last row that you see, right? From top to bottom there. And that's just because, again, since this is picking from ty, it starts at 1, whereas this one starts at 0, and it goes to the same number, so it's just going to pull 1 off the end. So we need to be able to look up our diffuse weight maps with the same thing that we were doing there, and that's the crucial bit. So that way, this sort of unpacking here where this all does its tx minus 1 nonsense and figures out where to put everything, that was all fine because we're looking up just by tx 4. So that's all fine, but we don't really have any way to recover from that ty problem, so we needed to make that be a minus 1. So let's go ahead and run it now, and we should, in theory, have a slightly better version here. And it looks all right, except I'm not sure why we're not getting any lighting on the actual character. That seems a little weird, because we see it's kind of a little bit strange, right? So that looks a little bit busted still, but the actual lighting of the world seems correct. So I'm not sure how exactly that's happening. That might just be because of the way that could just be randomly sort of the way that the character is, because at the moment, right, there's no bounce lighting whatsoever on anything. So, depending on exactly where the character is relative to how you're viewing it, right, you can kind of see as it goes there. So that might be okay. I'm not really willing to say it is or isn't at the moment, but I'm really kind of only looking at the environment. And so that looks pretty good, right? I mean, if I look at the way the lighting is flowing, again, looks pretty reasonable. We do have a problem with the way the voxel is aligned, and we have to look at that at some point. So do you see like that there? That's because our voxel is not aligned to where the view is, right? It's aligned to the simulation region, and that's like very unhelpful. So do you see this box here? This box is the thing that contains our lighting. So that always has to be centered around the view if we want to make sure that there isn't a cutoff in lighting. But at the moment it's not. And so when it switches to the simulation center like that, it's just a real issue, because sometimes the simulation center might be at the exact center like that and everything's fine. Other times the simulation center is shifted to like here. Now, one thing I don't know, and it's probably worth exploring, is if we look at what's going on here, it's kind of an open question as to why the simulation center got set there. Because the simulation center should be centered around the room that we're in, and for some reason, the simulation center, as you can see, appears to be I don't even know what's going on with the simulation center there. But either way, this is not helpful, right? And so a couple of those things are just now in a janky state. And that's okay, because it doesn't affect our lighting computations at all. So it's not something we need to fix immediately. It doesn't affect any other part of the algorithm, so we can leave it to fix till later. But it's worth noting that we do have issues with that we want to address. So I think we're okay for now with like the way the lighting is working here. And I think the next natural step is, of course, to try and get this working with some actual bounce lighting now. And so what we want to be able to do now, since this is what we're sending down here, is this diffuse map. And what we want to be able to do now is that diffuse map needs to get used in our actual code path where we sample the lighting to figure out what the lighting is on things that we hit in the environment, right? And so, again, just like looking at what's happening here, right? This is just a test where we spam some light into the environment with a specific normal. And it's really just a test of the voxel interpolation and the octahedral map, right? It's just something to tell us if we're working vaguely correctly. But it's totally wrong and doesn't actually talk about what the light is actually doing there much at all. And also, by the way, let me just run our test sphere as well through here so that we can verify that that's giving proper values. So here's our test sphere. You can kind of see that just doing a fall off light on the actual sphere, looks fairly reasonable. Because remember, basically what this is doing is anywhere that we hit, it's just basically looking to see how much light bounces back from a sphere that's like right here. And so it's, it's like a cosine weighting kind of a thing. Now, I don't, again, actually know that we're totally correct at this point because we might be getting a little bit too much specular. I'm not sure. I'm not sure how diffuse this should be. I'd have to go through and kind of think about exactly what should be happening in terms of that cosine fall-off curve, because since there is no indirect lighting, it's kind of hard for me to think about exactly what we should be getting, since we've got two cosine fall-offs in there, one from the actual light distribution that we stick in there, and then one from the actual diffuse. So I'm not exactly sure what the correct thing to see in this case is. Also, our clamping of lighting is a little aggressive here, and so I think I'm going to go ahead and get rid of a little of that clamping, just so we can, like this right here. This right. Where's our clamp? Here it is. So this right here where we clamp 0, 1 is not super helpful. So I probably want to clamp to something higher than 1, because overbrighting the light is actually desirable in a lot of cases. So we probably don't want to clamp it in that way. Like if we were going to clamp it, we'd tone map it or do something like that. But clamping 0 to 1 is not really good. So what I'd rather do here is say, okay, let's let this light go a little bit higher. You can see we've got a clamp min max here. So I think I'm just going to say, all right, let's clamp this between 0 and double bright. I mean, I don't know what we want to do there in the long term. We might want to just have a tone map where we map values in some kind of way. But you can see that adds a little bit more character to the lighting. That's still not probably enough. I'd go higher than that in terms of overbrighting. See, that just looks better, right? Because it allows you to get a light source that actually like whitens things up a bit past what their base value is. So it's actually kind of like adding in a little bit of extra light there. And that seems reasonable to me. Yeah. I'm not sure what the clamped out value should be, but that seems maybe more like it. And then, like eventually if we want to put some tone mapping in there, we can. But at the moment, we would just turn like down the brightness of a light. Anyway, that's looking really nice. I mean, again, we probably still have some bugs in there. And at some point, we're going to have to do like a really hardcore evaluation pass on this probably. But at the moment, at least as far as I can tell, there's enough certainty that this is at least roughly reproducing the light field we put into it that I think we could start to work on the indirect pass and get that working, right? That way we at least have everything working, and then we can start to do our sort of tune-up of getting everything debugged, right? All right, so let's see. And also speed optimize, because right now that diffuse pass is really expensive, and I don't know, we may need to do something separable there, or because there's just too many flops in that conversion from the specular sample to the diffuse. We don't really have a way of making that work at the moment fast enough. So although the game appears to be running reasonably well, you have to keep in mind that this is running at only 30 frames a second. This isn't hitting 60 right now. And it's not hitting 60 even though we're not doing the raycasting, right? So if we were to actually turn the raycasting on, which doesn't quite work yet because we haven't actually gone through and gotten the sampling in there, we would have an issue. Let me do test sphere. Where's my test? Oh, I'm in the wrong file. So if we were to turn these off and we actually run the full cast path here, what's the problem? Lighting solution. What am I getting complaints on? What's full cast expect? It expects the lighting work. That's what it expects. All right. So here's running the indirect pass, and just what you can see is like, to see how that frame rate really tanks, right? And so the problem that we're going to have, also, I'm not sure what's going on. I don't know why everything is full bright right now. That's total mystery to me. So, but either way, so with the full cast on, you can see the speed is just horrible, right? So the problem is I don't think we are going to have the budget for doing indirect ray casting plus that really expensive diffuse. Those two things together are just, either one of them is what we can afford and not both. So we need to speed either both of them up, or we need to at least speed up the diffuse one, because the diffuse one we've looked at quite a bit less than the ray casting, which is already going considerably accelerated over its base rate of just a naive implementation. And so, I guess I would just say this is, that's where we're at, right? So we have issues there. Okay. So I'm not sure why that was actually full brighting. That's kind of a surprise to me. I'm not sure what we're actually seeing there. Also, I'm not sure why we're not seeing anything in here. I'm a little bit tempted to take a look at the, well, you know what? It might be that we just left some debug code in there, but it's saying like I'm a little bit tempted to take a look at what this texture actually is, because I'm not sure why it doesn't show up as white or something in here. So that's a little bit strange. But again, we haven't really looked at this code in a little bit. So let's just go in and see what's going on there. So here's the full cast code, and basically this is the code that we're calling if we wanted to stick stuff into the voxel that actually gets updated via raycasting rather than, or via distributed raycasting rather than just like a single cast towards the light to see if you hit it. And what we get here is we can see that we come through here, we've got our old Moonlight that's going to be placed in, and we can turn off the Moonlight for now to avoid that being anything that is going to cause us a problem. You can see that the only place that actually comes in here is when we have light information coming down a path where we haven't hit anything at all, right? So our ray escapes the scene entirely, and we put the Moonlight in there. So we can get rid of that for now, and the easiest way to do that is just the moon color here, right? We can turn off. So we can just say like, moon color equals nothing, and then the moon is turned off, and we can eliminate that from the view. And if we turn that off, then I don't see anything different. And you know what? I saw some light in there, so it looks like actually all that's happening is the light's just building up till infinite values, probably something like that. So that's fine. So here's that casting code, and what you can see here is it's going through this thing and doing a bias towards light version of the sampling here, where we get this light leaf. I'm not sure I really want to do that. I think I might rather just not do any light biasing at the moment. So this kind of situation I might want to turn off at the immediate moment. And what you can see here is that the way that startup works is we then start picking at the end, or at least I thought we did. Maybe this is busted. I thought we were looking up ray directions here. So where does that... So it looks like ray origin is not getting updated at all. So this is just kind of garbage. Oh, no, it's not. Sorry. Ray direction is the only thing that needs to get updated. What am I talking about? So that's the part that we actually pick the new one, right? The sampling sphere with ray bundle index. And that just goes through and picks each one of these out. And I don't know that I actually want to do this add padding yet. So what I'm going to do here, again, is just, I'm not going to bias towards the light source at the moment. I'm going to go ahead and put this at the top, like so. Oops. So that we're actually not biasing towards light sources. We'll do that later. Okay. So here's this running without bias towards light sources. And what you notice is it lights very quickly, and so it's already a little suspicious. Oops. Try it one more time. I lied. There we go. All right. So what you can see is we're getting still a lot of light coming in there, and I'm not really sure why we're getting so much. So that's one thing that I want to look at. If we go to the update voxel call, you can see here that what this is doing is a slow blend. Each time we do an update, which is like this, it's doing a slow blend towards whatever the lighting information is that we have here. And so one of the things that I don't really want to do yet, but that we'll do eventually, is make sure that our actual light, our point distribution actually tries to get different directions on the octahedral map each time. But that's kind of a separate issue. So the real question we want to ask now is, when we do this raycast, why are we in a situation where the things that come out of here are represent too much light? I assume that if transfer PPS is set to nothing, so we're not trying to stuff any actual light into this thing, that it would just remain dark, right? So, there it is. If we were trying to transmit a low amount of light, so, we're going to transmit some white light, let's say, and we're just using a quarter light transmission, so, not anything particularly large, then I would imagine that we should stay at a reasonable value, right? And I guess the only thing I'm not sure about here is if that's the transfer photons per second that we're seeing here, I'm not sure why that got so bright, right? So I am a little confused about what's going on here. So we may want to dig into that a little bit first, because I'm just to get my head oriented around it. Again, it's been a while. So if I look at update voxel, and we just look at how much light is getting thrown in there, in theory, right, that should always go towards this value, which means that at least in theory, that this is the expected result, right? And my assumption is that if that was actually true, meaning if this is actually working properly right now, and in fact, but I kind of know it isn't. So look at what's happening there. Do you see how it gradually gets brighter like that? So why is that happening? That's just really confusing. Because if we're always blending towards this value, always, something's not right here. Because this lerp should always be pushing us towards this one value, but that's not what's happening. So we've got some issue where we're, I think we must be doing something in the light sea itself that we shouldn't be doing. So let's just go take a look at what's happening there. So where is this? Who's actually touching these values? So, for example, do you see this here, right? Although this one here, this is doing an update voxel. So what are we doing differently? So this update voxel, right, is going slowly towards a particular value as well, but we're not getting that weird bloom. So let me just indulge me for a second here. If we switch to our test case, right, which is this is a test caster, and I run it, here's me jumping around with my test caster, right, and it seems to be working okay. If we're in the test caster, and now I was to say, all right, the test caster is just going to output a flat value now, right? So the same situation I was just testing in there. Right here where we go to do update voxel, instead of actually doing any kind of lighting, I'm just going to do a gray that is a constant value. What happens to my light? Okay. So I thought I was doing exactly the same thing. What happens if I do this lots of times? It shouldn't do anything different. And it doesn't. So you can see that something's up, like something about that pass it's like we're doing something different in that pass such that that test code is failing there, meaning that output of just a straightforward value is not working. And I'm not sure why that would be. So you can see that we've got some kind of a weird bug happening here. And I don't know what it is. So when we actually do our full cast, we're getting just a much brighter value, but I don't know why. And so we're going to have to figure out what's happening there, because that shouldn't be happening, right? So when we actually do the full cast, the light D value we don't use. The octahedral offset shouldn't really much matter. Oh, but it does. So here's the thing. The fact that this is setting the light incoming from multiple octahedral offsets would produce this result. So having 0.25 amount of light in all of the directions, I guess that's, and then the cosine fall off summation that we had turns out giving you this if you have a flat quarter light coming in everywhere. I guess. I'm still not 100% convinced of that though. But it seems like that's the only real explanation. I don't see really any other explanation for it. So I assume that must be right. Again, kind of hard to say, so I'm not sure what to make of it exactly. But when you have the light coming in from all directions, yeah, it's going to sum to something higher. Now, I don't know, does that mean my coefficients are busted though? Because it doesn't seem like that much light should be getting in there. I wonder if my summation, so if we look at that diffuse map build, is that actually using incorrect values, right? And I don't know. So we should probably look at what these actually are. It looks like a standard cosine fall off curve, right? And it's clamped. So it should be something that, for the most part, is exactly what you would expect. So let me just go into that build diffuse light maps and take a look at what some of these light maps actually are, right? Because I just want to see if those values make sense to me, because I don't really know. My intuition is I'm a little confused about why a cosine fall off filter on our incoming light would produce such a bright value for a flat known amount getting shoved in there, right? That's the thing that's making me confused. And it's possible that it's correct. I don't know that it's wrong. But I just don't know that it's right either. And so I want to investigate a little. So if I run this here and I go to the full cast. So here's where we're doing what we're doing. I just want to go to the solution itself here. There we go. We got tons of threads right now. I'm going to go to the solution here. And I just want to look and see for the diffuse map itself, which is this diffuse weight map here. I just want to look and see what kinds of values are in here. So here's a particular entry into the diffuse map. It's 0, 0, right? And here's like the examples of the values. This is kind of hard to read, isn't it? So, I mean, I guess what you can see is the fall, like there is a lot of 1 values in here. Like if you just look at the fall off, it's like 1, 0.9, 0.6, right? And that's so So yeah, I mean, that does make a fair bit of sense. I guess if we're actually looking at what the transmission should be, I'm trying to think if this is wrong or right, but so the amount of light that's bounced off of this thing properly summed over the hemisphere. I mean, is that actually correct? I guess one way to look at it would be if we assume that we only had one light. Yeah, so I think there is a fundamental misunderstanding here, perhaps by me. I think we might want to look at just. Let me just work through an example for my own edification. I'm going to get the drawing tablet here. And let me just see, because I'm not convinced that actually, I'm not convinced that we've actually got this equation right for the transmission. And I just want to, because I've never looked at it quite this way before, where we're actually doing it as a filter. So what we've got here is, if you look at what's coming in, I want to just see what the example would be in the case where we've got a single light source that's getting applied to one of our diffuse maps, right? So we effectively have a specular map that we're computing. So this is like the input, right? And then we have the diffuse map that we're outputting, and this is like the output, right? And so if we have a single pixel light source, so, you know, there's a single direction that hits this light, right? Then inside the diffuse map, what we're going to have is this light, if it's directly on, the diffuse map here is going to say, well, all right, for any given pixel, I'm going to sum the hemisphere area in here, which, you know, probably looks like something like this, right? And only one of those pixels actually has any data in it. So even if my coefficient is 1 for that pixel, well, I know it's not going to get any brighter, so I'm just going to write it in there, right? So the outgoing transmittance for whichever pixel I was looking at, which, you know, in this case would have a 1-to-1 correspondence here. This one will just get full bright, and this one will get like slightly less bright, right, around it, right? So in the case of a single light source, it seems correct, and I guess the interesting thing there is, I think we sort of have at least a little bit of verification that that was true, because in the case where we were only filling in one direction, the filter worked just fine. So now the question is, well, what if we actually have two? So let's suppose we have two lights, one here and one here, and now we want to know what this would be. It's going to be this one plus this one times like 0.9, right? So they're going to be pretty close. And the question is that correct, right? I mean, is this what we expect to see? So what's actually happening here? Well, if we have a surface, and this right here, this diffuse map, is basically asking how much light is leaving the surface at this point, right? I'm sorry, in this direction. So if we assume that this here corresponds to this, right? Oh, wait, so there's at least one bug here, which is that we're not using the reflection, are we? So we're doing one thing wrong, aren't we, here, which is that we're computing the transmission as if both of these are the same, and that's not right. So, okay. So, okay. So the first things first. Here's our surface normal, right? And if we're talking about producing a thing that says we want to be able to sample, these kind of rays from whatever our surface normal is, and then we want the diffuse map to tell us what direction things were going off in, right? Then if we're talking about these directions, it seems like we need to talk about the transmittance function as being actually doing the bounce, right? Because if we were like, well, here's this direction here and this direction here, we're actually just taking the inner product of these two, but we want to actually take the inner product of, if we're looking in this direction, we want this thing to bounce out this way, and we want to take the inner product of the reflection, right? So that's kind of a bug, right? But in addition, we're also not taking into account the incoming cosine. So the thing that comes in from this angle, for example, should have already been directionally cosigned away, I believe. And it's not being. So we've got two bugs, I think. The first bug is that the incoming light direction needs to get cosigned by whatever the incidence on the normal is. And I guess I'm not sure how to do that because we don't have a normal in this case. I mean, am I wrong about that? Because since this is a light map, I guess the problem is since this is a light probe, right? It's a thing that's sitting in space that's just like sending out rays in different directions. And all it knows is it saw a particular amount of light coming in here, right? So I guess the problem, unless I'm missing something, is how would you compute the hemisphere? Oh, but that's okay because you're doing it now. You're trying to compute as if you had a hemisphere for the normal. So you do know what the normal is. You do know what the normal is. And so what you're doing is you're taking the inner product of each of these, right? And saying we're going to assume that this much light bounces out along the normal to this surface based on the incoming here. That seems right? Am I totally wrong on that? I'm not sure. But, right, I mean, think about that for a second. So what we're actually doing is pretending we have a surface, and we're saying, let's suppose we have a surface that was passing through, and this was the normal. And all of this stuff, right? So all of this stuff is now not considered. And that's correct because that would happen with this inner product. And all of the stuff in here is considered, and it's going to be considered based on how much light would bounce out in this direction. And that, I guess, is the incoming light. It bounces out here, and then presumably that's just the inner product of these two for Lambertian anyway, which is what we're doing. So I guess this is so I'm reasonably comfortable with that, right? And I guess we would just say, well, if all of this light actually wasn't coming in from all of these directions, it would actually be fairly bright. Probably, I would assume. But that actually does look correct. I mean, that looks like what it should be. I'm not sure that I'm not seeing anything weird about that, right? It looks pretty good. Or does it? I'm going to go with yeah. I mean, I don't see anything particularly weird there. That looks pretty much right to me. So I don't see a lot of error with that. And then when we're actually doing our lighting sampling, I guess that is one thing I'm not sure about here. Let me just take a look at that Z-bias program. I don't really remember exactly how we processed the light once we sampled it. So you can see here where we were doing like our texel fetches, and we, combine them. We have a couple different ways we tried combining them, but either way, we're doing a fetch and we're combining our light sources. And once we actually get that value back, I guess what I would say is, you look at the sample lighting here, we're pulling out things from the octahedral map. So you can see us doing that here. We blend them together. And I guess once we get that sort of back, we're not accounting for the bounce off of this surface. So I do think we're missing a cosine term here. I could be wrong about that, but if you think about what's going on in this sampling, we just have a thing that's like how much light is would be leaving in the direction of this, in this probe in this particular direction, right? Or I shouldn't say how much is leaving. This is how much is incident on this hemisphere, right? With this particular normal. And so if we want to know how much light bounces off of that, we would have to actually take into account the direction we're looking. We'd have to actually modulate it by I don't know. We'd have to actually modulate it, right, by the cosine of that angle, I would think. This is really tricky. And the reason is because it's hard for me to really wrap my head around what it is we're storing in this map, right? So maybe I have to work through the entire sampling. So let's see. What would we do if, let's suppose we've got an actual surface we're trying to sample. So I have a surface. Here's the normal. I'm looking in this direction, right? So here's my eye. Well, I should say eyes, because, yeah, I mean, I've got two eyes. So the eyes are looking in this direction. And then, so we want to know, right, we're trying to produce like a lobe. So most lighting, right, would look like something like this. Or something like that, right? So we're producing a fair amount of light coming from this direction and less from other directions and so on and so forth, right? So we're trying to figure out what the light is in this direction. And so we go to our light probe and we say, oh, hello, Mr. Probe, right? Tell me what that same direction is for you. And we're going to use that value and pretend that that's how much light is coming in here, right? But if that's how much light, but we have a couple different things, right? That's how much light is coming in this direction, but we also want to know all of these other directions, right? So the specular probe would have told us that, but we want kind of a summation of cosine curves around this guy for, the hemisphere as well. I guess sampling, if we were to sample the specular map a bunch of times with cosine fall off, that's what we would get. But what we're trying to do here, I guess, is approximate what happens with this equation. And so for diffuse lighting, I guess what we're trying to say is, well, what's the average outgoing? So we are actually trying to roll that into our pre-calc, right? So that would mean we actually want to roll in how much bounces out in a particular direction for... Or how much is generally radiated out from the surface, and that radiative transfer there is going to be based on the actual reflection amount for each of the incomings, right? So once we have that and we want to sample that from somewhere, I mean, it is generally true that less should exit depending on where, if you're looking flat at it, you should get more, right? Is that actually true? I mean, not really, because if you assume that it's radiating light evenly in all directions, then it's only the initial bounce that takes a little bit of the light away, and then it's just scattering in all directions. That's the point. But I also guess that in this case, you would say, well, as the light comes out at you, you would be losing some. Where's Don Mitchell when you need him? Probably researching a space program. That's usually what he's doing. So yeah, I'm just not sure. I'm not sure about this. This is one of those things that I find really difficult. I wish I was better with lighting equations, because I think what we would need to do here is actually write out the equation for what we would be doing if we were actually sampling the entire thing correctly. And then we need to see how we make our diffuse map as close as possible to what that would actually be, right? And I'm just not sure. I'm just not sure what those coefficients should be. Like in this particular piece of code here, right? I just don't really know. Like, this is taking out that initial amount, the bounce. So the bounce footprint, this part. So the size of the actual like microsurface off of which the light bounces, that's that initial cosine term. So that's the cosine of the angle here. But I don't know if there's, and we're summing all of those up. So we're taking into account for each incoming light direction, we're taking into account the footprint, the microsurface footprint that it bounces off of. But what I'm just not sure of is then when we go to sample it with an actual surface, do we actually need to take into account anything about that angle? And I just don't know. Because it's not really doing the right thing. I mean, I'm not sure how to state this in another way, but we're taking a map that was computed by taking a summation of the incoming light source with the cosine footprint for some direction. And then we've got a surface normal, like this, that then bounces light, and we're then saying, well, okay, actually I should do this exactly right. So we're taking then a view direction, and we're bouncing light. We're saying, okay, this direction and this direction are the same, or they're close to the same, because it's octahedral map, so it's not going to be exact, but we're interpolating to get it. And so we're going to take all of what that incident light was here and assume that that is what you would be getting, right? It's assuming that that's what light was coming in here. And that's not correct. Oh. So, but the only reason it's not correct is because we're using this direction and not this. If we were actually using this, it would be correct for a Lambertian surface. So actually, he says, maybe all we really needed to do was say this part here actually should just be the normal. So like the R value here should actually just be this. Right? So that is what for diffuse lighting, which is what we were sampling from a diffuse map, it actually should be that, meaning it should look at the normal, not the reflection vector, because the reflection vector is not what the diffuse map actually captures, right? The specular map captures that. Let me go ahead and change back here. So that would also mean, let me go ahead and let me just run the test sphere or the test cast through here. There we go. So that would also explain where we're getting sort of some weird lookups in there. Oh, I should run the test sphere actually too. So if we actually look at what's happening, where's my test cast? That looks like the test cast is still doing this nonsense. There we go. So that should be more correct in terms of diffuse lighting, right? And let's actually try the test sphere because that's the one that actually has the directionality to it. So the test cast is not really correct for this test. We want those. There we go. And that's what we would expect now. So I think that's right, and that's all good. Unfortunately, this gives us really no insight into our other problem. Now, it's worth noting that we should send down both maps, right? Like, we should send down the other map as well, because the other map would be good for specular sampling, so we could add some reflection in there, which we probably want to do at some point. But now you can kind of see if we're just sampling based on the normal, now it removes that directionality, which is what we would expect. So that's why I was like uncomfortable with that before. It's like, yeah, duh. Like if you're trying to sample a diffuse map, you can't use a reflection vector because you couldn't possibly have computed what that should be into a diffuse map because you would have needed to know the normal of the surface first, which we wouldn't have known. So since we know now, it's like, oh, right, we're trying to sample diffuse, so you sample by the normal. That all seems reasonable. Okay, unfortunately, that doesn't really give us much information about what I was actually wondering, which is the other thing correct? Where our transfer PPS here, right? And again, it sort of seems like it must be. I don't know. Like, I'm still a little nervous about it, but I guess it just means if you have that much actual incoming light in your environment, you're okay. I don't know if that's really true. I feel like it probably means that there's like maybe the fact that it might be a light fall off issue, would be the other possibility. So one of the things I guess that I'm not sure about is where does fall off come into this, right? And so when we're looking at surface to surface transmission, the ray casting itself kind of does fall off in a sense. Because if you're looking at how many rays could possibly hit like a light source, that is accounted for in the ray casting. So it may be that actually this is what you would expect, right? I'm just not sure. And so one thing, let me just make sure, let me do a couple of tests to make sure that it's even plausibly right. What if I should be able to reduce this number down to something that doesn't get super bright, right? And that is, so I don't know. I don't know what to make of that. I'm also not sure I understand why this is still showing some reasonable amount of lighting and yet everything in our world is dark. So that seems a little wrong, doesn't it? Wouldn't you say? Oh no, you know what that is? Because we clamp our lighting down to get better edge interpolation. So that's all right. So I guess I'm going to go with that seems okay, honestly. So let's assume that that's not an error. And let's try to get this thing working. So if we get rid of this, then I'm assuming our immediate problem is just that our transfer PPS code is kind of garbage, and we end up in a ridiculous, like, we're pumping way too much light into there. We know we turned off the moon color, so in theory we should not. So there's the moon color, right? We know in theory we shouldn't be pushing any in here. So basically what we're looking at here is this path through the code. Now, at least in theory, when we look at what's getting summed here, so you look at the transfer PPS, that transfer PPS is getting done in here. So in theory anyway, if we just got rid of this, I don't know what this light fall off is there for. Probably old school code where we were actually passing that into the voxel. If we just get rid of this, we should get no lighting, right? I mean, in other words, we're initializing the value to 0, so we should get no lighting in the case where we nerf that, because all of the lighting should be coming from this path, right? And if we take a look at the moon color thing and I turn that back on, well, this would probably be too bright at this point. But if I turn back on the moon color, we should be able to, like, get the moon color filtered back in there at a reasonable rate, right? So here's the moon color, right? And let's take a look at what's going on with that. So it currently looks busted. Like, it looks like it's writing to the wrong location or something. I mean, you know what I'm saying? So maybe let's just start with the moon color and figure out, because that's just coming from a direction that's not getting sampled. So let's try to pull that together better. If I go over here and look at what's happening with the moon color, we have a moon P, which is basically saying where is the moon, and in this case, the moon it looks like just straight above us, just Z up, directly Z up, right? And so if we take a look at here, what's going on, we expect to see our get octahedral offset of the negative emission direction. So the emission direction here is this is the lookup here. So that's saying, all right, here's the ray direction, and I guess it wants to say what's coming back from, so I hit a point, I want to know what the emission is for the light probe in that area. So that makes sense. And then we're saying, well, we want to know what the negative of that was, right? Because we need the negative of that to figure out where we're going to put the light that we see in this direction, right? Because we're saying that's the way we were looking. So that seems correct, right? I mean, I don't see anything weird about that. And I guess what I would say is this equation just kind of looks wrong to me. The emission direction here, this is the look direction. So the emission direction, I think this needed to get negated, first of all, because we're actually doing a dot with the moon. And we say moon direction, we actually have one, so I think this code is just kind of busted. Yeah, that's more what we would expect. This code is kind of busted and wants to look at what the direction to the moon would be, I would think. So what we probably want to do is something more like this. I would say, like, the moon should have a moon direction. It's a directional light source, right? So I would say we probably want to take some direction, whatever that is, and maybe that direction is, something like a little bit of an over-the-shoulder kind of a feel. So let's say that it would be something like that, maybe. I don't know. Something like this. And then what we would want to do is say, well, we know the moon direction, and we know what direction we were looking, right? So what we'd like to do is take the inner product of those two. So we've got moon direction and emission direction. And again, we don't want the emission direction. We want the negative of that because this is the direction we're looking. Times the moon color. We can get rid of that to do. And that would give us a more proper use of the moon, I think. Oops. All right. Probe sample P equals moon P. Oh, interesting. So that's how we were doing that before. That makes sense. So probe sample P is done with what? That's not even a thing that we use here. So that should just be in here, looks like. Right? gonna get rid of these for now because I don't really know what I'm gonna. I can put in my looks fishy tests if I'm trying to look for something fishy again later, but so I'm not sure why this is so slow, but I assume it's just because we're still running the raycasting, right? Which, like I said, is expensive, and then we're also doing the diffuse. So that seems right. So now if I say, all right, how bright is the moonlight? And the moonlight is like that. I don't know why it was ×3, but probably because we had dimmer lights before. Just see what we get here. So we'll just put that right around the ambient floor. And that seems reasonable, right? I mean, I don't know if we'd actually want the moonlight to be that bright, but seems reasonable. So maybe a little darker. And so that's good. That just means our lighting is at least somewhat stable there. So we can pump an ambient into it and it's okay. Now, I'm not sure why we're getting, like, that's a little weird, right? So there's a little bit of a weird darkening that's happening here. And, oh, I know why. It's hitting the light source. Interesting. And we can see a little bit of flicker, so we know we're actually sampling the moonlight. Yeah, all right, you know, looks okay. And so now let's see if we can actually start to push some actual light through this. So here's us getting where we sampled the light from. Here's the normal. Here's our reference color, which is just whatever the surface we were bouncing off of was. And here's the emission level of that thing. And so then we want to do we want to see whether or not this thing was emissive or not, right? So this is the fall off bit here. So the 1 minus emission, and then we just go like, okay, take the emission direction and the probe sample normal. That's how much of the fall off we're going to have for emissive, I guess. And you can see us actually using that here. So this is basically a linear blend, right, between those two. Well, it's not really linear blend, but sort of is. So I think that all just works out. I mean, that seems all correct to me. Not certain. Sample D is already the emission direction. So I'm not sure what sample D would be used for here. If I'm looking at it, it just looks... all of this stuff looks a little questionable. So ray.n, that's correct. That's where we hit. That's the normal of the surface we hit. Sample D is, or we already have that, right? Sample D is just the emission direction. So that doesn't really make any sense. I'm not sure what... Yeah, so let's think about this. So we've hit a surface, and at that surface, we want to know what the emission direction was from there. So this actually is not right anyway. This was just supposed to be emission direction, right? Because we're supposed to say, at this point, with this normal, what would you have bounced in this direction? Pretty sure. Right? And the answer in this case would be that you would just bounce. It doesn't actually matter, right? Meaning you wouldn't care because they're all Lambertian, so you would just say you're going to get this much no matter what direction you're looking, right? I want to say. I mean, am I wrong about that? Because it should just be whatever the diffuse map says at that point. You shouldn't actually need the emission direction. Again, this is where I'd like Don Mitchell. Don, help us. Oh well. He can't hear us. So yeah, that my only question there is I'm going to continue passing this down, but I don't actually know that I don't know that there's anywhere in the equations for what we're doing right now to actually have that happen, right? So when we do compute voxel irradiance at and we say P and N, here we want to go like outgoing, right? So which direction we're actually looking at or trying to look at. And we're pretty much not, we're not probably going to use this. So if we take a look at what's going on here, we're going to need to do this computation exactly the way that it would be done. And you can see us doing it here. We're looking up the voxel information. We don't actually want to do this R anymore. So I'm pretty sure this is exactly analogous to the other case where we just want to know in the normal direction, what does that map give us? This is not what we want. What we actually want to be doing is sampling our other map, right? We want to be sampling the actual texture map here. And that's what we want to be outputting. So this part is incorrect. And the weird part to me, and the reason this is a little confusing now, is that this should actually give us back, this must be wrong, this code must be busted. Because this should always be giving us back a lot less light than the diffuse map would. So if all we've got is specular to bounce around here, I would think that would produce totally, like, way less light. But the opposite appears to be true. So I don't know what to make of that. So we're going to have to step through this code probably and figure out what the heck's going on, because that doesn't really make any sense. It should be producing low amounts of light, but instead it's producing super high amounts of light, right? Like those are all really high light values. You know what I'm saying? So what's up with that? What is up with that? Because everything I would think should indicate that we should be getting a lot less light into this thing. And instead we're getting a lot more light into this thing. I guess one question would be, do we ever clear this thing properly? I assume we do. But it's just weird that we're getting any light at all. We should be getting really low amounts of light, because without the diffuse summation in there, we should only be able to get light sources if we actually bounce directly towards them. And so there should be a lot less light, because diffuse surfaces are things that help light the whole environment. So we shouldn't be yeah. So that's pretty bizarre, and I do wonder if our compute voxel irradiance at function is kind of busted. I don't really know. So let's take these things out sort of one by one. If I go to the compute voxel irradiance function and just stuff it to produce something that's just a flat light, like so. My first question would be, is a flat light going to still have these errors? Because if it was, then it's not actually our light sampling, it's some other aspect, right? All right, so I guess I'll basically say that that is somewhat surprising. I guess the reason for that is because the emission interesting. So we're actually still getting the lighting because the emission, if you hit an emitter, it's going to put emission into the system. And if you hit anything else, it's going to put bounce lighting into the system. And so in this particular case, that turns out actually giving you some lighting, right? Which is real weird. And so I guess that's just giving you a single bounce light with no movement of the light throughout the scene. Looks kind of cool, though. I can tell you that. I say. So let me go ahead and knock out the Moonlight one more time. And just like, yeah, there we go. Right? Interesting. So that wasn't exactly what I expected to see. I was kind of expecting to see something more related to yeah, that's just very surprising. But I guess that makes sense because we do have single bounce lighting now that's actually computing all this lighting properly. So it's like, oh, you can see this light on this surface and all that stuff. And like, wow, okay, it's better than I thought it would be. So adding the Moonlight back in, that all looks right. And so the only question is now, why is our compute voxel or radiance kicking back such ridiculous values? Or is it just that we're overloading the light somehow? Because it's specular, I'm assuming it's got to just be a bug, and it's busted, but I don't really know. So let's take a look at what we're doing here. We're doing a mapping of the sample position. As you can see here, we're taking wherever the sample is, taking the corner out of it, doing a offset by the center. Oh, no, that's right. So we're multiplying by the inverse dim first and then doing an offset to get us back to the center. We're then doing a floor. I'll be honest, that doesn't look right to me. So the inverse voxel cell dim, this puts us into... Yeah, so if we're flooring, I feel like that should have been a plus. Let me just double check something. Oh, what am I going to double check? Duh. That's not going to do nothing. We're not running this path. Yeah, so it's a little confusing. The invoxel cell dim there. Something's a little iffy. Because this is saying, all right, where are we relative to the corner? Now, which cell are we in, right? And if we floored that, that would just give us which cell that we're in. But we're subtracting the 0.5 to offset by the center, which, by the way, looks wrong there too. Let me just see, because we're doing that in here, right? So we're doing that in here too, I assume. For our Vox I. Yeah. So in here where we do our Vox UVW, so to produce our Vox I, we just use the floor. And so I wonder if that's actually wrong then, because we've got, I wonder if that 0.5 should actually be in there here. So the Vox rel P, when we actually do the, when we actually do this stuff here, right? I wonder if this should actually be a minus. I wonder if this guy should actually have this in here. Let's see. Just want to see what happens. Oh. Oh, wait. Sorry. That's the Vox inf total dim times the relative P. So that's actually giving you the full map inside. So I didn't really want to do that. So I guess I actually want it here. Yeah. So now you can kind of see that the light is actually centered properly. So I guess that was actually a bug in the shader code. Because remember, the light was looking like it was off to the side a little bit. So we actually were looking it up incorrectly there, which was a screw up on my part, right? So this is actually what it should look like, and now you can kind of see, yeah. Now, already, it's so fascinating too, right? Like, we didn't do any work to make Moonlight not show up downstairs, but the reason it's not showing up is because there's actually a floor above us, so it can't find the moon, which is pretty cool. I don't know how we're going to maintain that all the time because there's places now, if you go, there's nothing above it. So I don't know that that's a long-term solution. Like, so here the Moonlight is getting in because there's nothing above this, right? And furthermore, it's a little weird because there's like shadow over here because there is something above it there, right? So we kind of need to put ceilings on things if we wanted that to actually happen. But it's kind of cool, right? And this is why simulation is always interesting because you get natural, interesting effects out of it. And it's just pretty interesting. All right, so I guess, this was actually correct, and we just hadn't thought it through in our actual shader. So this is right. And you can see us doing it here. So we're doing the invox seldom here, and then subtracting that so that we end up with our actual indices. So here we look up our voxel index. Our UVW is the F chord minus the actual remultiplication of this thing, which that all seems right to me. That should come out okay. Then we're actually doing a lookup of the voxel by taking all of the different offsets, same as we were doing, right? And so we have all those cell pointers now. Then we're just saying, all right, let's go ahead and get the octahedral offset, lerp the results together, and off we go. Well, this is wrong. Is it? Or no, it's not. So this is always between x's. So that's fine. And then this is y's, and the z is the interior. So I guess I'm not sure what's broken about that. Let me try knocking it down a little bit just so we can see if it's a lighting amount problem. And just so I can play with those levels a little bit. So let me go ahead and run that. Here's it running. And even with it knocked down quite a bit, it still gets out of hand. So it feels like there must be something wrong with that computation. But I don't know, obviously. So here's with it knocked down dramatically, right? And let me go ahead and knock it up a little bit just to see where the explosion point is, just for my edification. So you can see it's like really just behaving. It really kind of feeds back on itself, right? Even at very low levels. Which I would assume just means mostly that we've forgotten some kind of damping, right? Like we're not thinking about this in terms of photons per second flowing through this thing the way we were thinking about it before. And we're not using the diffuse map yet, so obviously that's a difference. But just why you would need to damp this down all the way to like basically at least there, it might even be a little lower than there, in order to get that to not feed back is confusing, right? Like that still feeds back. Right, all the way out. So we at least know what it is that's happening, right? It is the fact that light is our lighting equation. We had this when we first did it too, when we first did our distributor. We had exactly the same problem, right? And you can see, like, it gets these like, oh, I got transferred a certain amount of light and that light was too much or whatever, right? And so we're not conceiving of the photons per second anymore the way that we should. Like, we've got an issue with how that's being looked at, right? And I'm going to have to remember kind of how we conceptualize that to make sure that we don't have that problem. So when we talk about how many photons per second are flowing through something, I guess the problem is that thing, well, we're always blending towards a value, though. So that's a little weird. So, yeah, I mean, the interesting thing is we're always blending towards a new photons per second value, right? So what would cause that value to creep upward like that? Because it should only be summing the light probe stuff. So somehow this produces values that are like growing, which I'm not sure why it would. So what's weirder to me still is that this produces values that are growing when you turn this on, but the version that actually adds the emission in does not, right? So this doesn't actually do that. So let me think about what this ref fall off thing is here. So first of all, I want to assert that emission is always less than or equal to 1. Like, I don't actually want to ever see anything where that's not the case. Good. So if emission is always, oh, and you know, these are all on, right? Just to make sure. Yeah. So we know that the ref fall off, if the emission's on, ref fall off will be 0. So it won't do anything here. And it will just add in the emission times whatever the emitter actually was doing. So assuming that the emission is off, so assuming emission is 0, then this will not add anything. And so we're talking about only the sample n times the emission direction. So we're talking about a fall off curve that's based on, you know, whatever the thing that that's pointing at us, and what direction we were actually trying to do an outgoing vector of. Now, I'm not sure that fall off actually is supposed to be there, because that should have already been accounted for by the diffuse map. So once we switch to the diffuse map, I'm not sure that actually is supposed to be there. But if we look at what happens with it, it can only reduce the transmission, right? It can only knock it down from what it was. So then when we multiply by here, that's never going to add energy into the system. It can only subtract it. So we really are just taking whatever the light sample is and multiplying it by the sample ref color, and the sample ref color, in theory, should never be above 1 either. I guess we could assert that too. And in fact, maybe we should. So maybe I should just do this. And run it. All right. So I just want to make sure there was no funny business. So when we get to compute voxel irradiance at, the question is, how is this taking a sum of photons per second transmission values and getting a number that's actually higher than any of the other photon transfer. And it's not necessarily doing that. I mean, it could be that the light is bouncing around. No, it is doing that because we've seen what the emission values are, and they're not that. So how is it doing that? How is it producing values that are going above the actual emission that we're introducing? So let's try this. I'm curious to know. So let's suppose we set the emission value to 0 everywhere, right? So we just said, look, there's no emission ever. So the moonlight is all you get, right? That's it. So here we are hopping around, right? And we're just moonlight. So we're able to convect moonlight around now if we want to, right? But that's all. And so then we go into this voxel radiance function, and I delete the damping, so there's just moonlight around. What happens with just that? So, all right. This should give us a way to debug this program, right? Because here's what's happening. Nothing we're ever injecting into this system, ever, is now going to be above the moon color, which is super low, right? It's this, at maximum, 0.1 brightness. So if we're injecting such little light into the system, how can something that only returns the lerp of at most that value return something greater than that value? How is that happening? Do you see what I'm saying? Like, to me, that says we definitely have a bug here, right? Like, something really bad is happening, and I just don't know where. So there's a couple places that this could be happening. One, it could be happening inside the octahedral map by sampling something erroneous. So let's say we've got like an off error. These are somehow bogus values. I'm not sure. And we're sampling off the end of this thing and grabbing garbage or something like that. We could have a math bug where this lerp is not right. But basically what I want to find out is how are we getting back values that are outside this range? So what I'm going to try doing is I'm going to try asserting here that my result is, let's say, less than or equal to 0.5. And so I just want to say, like, look, let's just say we know that this should never really be able to have produced anything even close to that. So just that should stop at some point, right? And it should return, it should like halt there because it has to, right? And maybe if we just do this in debug mode, then we can go look at what the various cells are that we were sampling, see what the actual values are, and how the heck we got a value that high, right? So again, just trying to figure out where my mistake is by paring it down. So go ahead and run it. Don't want to actually break here. And I'm just waiting for the assertion, which will be a while because this is the super slow path. Oops. There we go. And so now we can look at the results. We see that we've got absurdly high values in here. And so let's just see what we've got for our cell values, right? So here's our cells. We've got, yeah. Here's all of our cells. Right? So here's the light color. And I guess I forgot to look at which one we're looking at. So we're looking at 5.1, right in here. So TYTX, so, oops. Where did that go? Where did cells go? Did I delete it somehow? That was weird. So anyway, inside cells, let's look here. So we're looking at 5, 1. So there's no light coming in there. Maybe I should just pull these out to something easier for me to look at, but you know what? I can do it this way. So let me look up 0, 0, 0, light C, 5, 1. So there's the light here. There's the light there. So like all of this is nothing. So there must just be one of these that's weird. All right, so am I missing something? Like, we've got... What the heck? All right, that would do it. So, yeah, not great. So this is garbage right here is basically what we're looking at. Not our finest hour, to say the least. Not sure why, but let's take a look at how this was being calculated. So our blending coefficients are complete garbage. So let's take a look at our F chord here. So our F chord is supposed to be, well, let's start even a little before that. So sample P is where we're going. Like that's what we're supposed to be looking at. So here's the location in the world that we want to look at. And our solution Voxmin corner, that's the basis of the voxel, right? So this thing is definitely inside the voxel. Well, actually, I guess I don't know how large the voxel is, so maybe not. But at least point being, it's not on the min side of the voxel. So when we produce our F chord, we should get something centered around this thing times the invoxeldym. What is that invoxeldym, by the way? All right, so it's 0.7 is the celldym. So that's actually going to give us back the index into the voxel, and I don't know how big the voxel is, actually. Oh, I see what the problem is. This thing is outside the voxel. So we just don't, because our voxel ends up getting clamped. No, but that doesn't, no, that's wrong. Because this should still, we don't account for that anywhere, so it's fine. Right? Because we should still have produced another value here. All right, so let's just, hold on. Bear with me for 1 second. Let's just do this computation slightly differently so we can look at all the parts. So let's do our, like our base chord here. So this would be like the basis there, right? And this way we can say, like, look, this is where we're looking up, and here's how far away from the thing we're looking up we actually are, right? And go ahead and make sure that works. Now, also, we should double check the one in the Z-bias shader for this. So if we look at what happens inside the Z-bias program, I just want to make sure this one's working well as well. So when we floor vox I, yeah, so we do a floor and then we just do a subtract of these two things, right? Which is what you would expect. So actually, like when you look here, in fact, when you look here at this, I'm not sure why we're even doing this way. Why is this getting multiplied out? So I think that was most of our only problem. That was probably our only problem, right? This is the actual equation, right? We just had the length in there for no reason. But I think that's all we actually need. And let's just verify that real quick. Yeah, there we go. How do I get this thing to... Oh, this is the release mode. All right. Wait, no, it's not. It's not release mode. I guess this is just having trouble with threading. Run to there, please. What's going on? There we go. So let me just look at the UVW values now. So that's more what we would expect, right? Okay. So that sure seemed like our problem. Why this is always at 0.5, I don't know, but probably because we have particular heights for off the ground that our things are or whatever, but that's a separate issue. So anyway, I still think we want to look at this code a little more carefully, but I'm going to run it now just to see what the result is, because we are out of time for today, and tomorrow we can start looking at it more carefully, but I just want to see what's going on here. All right, so good. Now we're actually in a state where things make a lot more sense. That's what I would have expected to see when we are not injecting any emission into the system and it's just the Moonlight, right? And so now if I turn the emission back on, hopefully we get something at least a little more sane so that we can be in a better debugging, stronger debugging situation starting tomorrow. Okay. So that's like way more sane, right? I mean, that looks a lot more like a reasonable lighting computation. And the transfer is now much more stable, right? Okay. So our biggest problem now is just that we're not actually using a diffuse map for sampling the lighting for our bounce lighting, so it's all kind of garbage. And so the biggest thing we kind of need to do there is just make sure we can actually get an actual emissive, an actual diffuse map for that. But otherwise, I think we're in good shape now. This is nice and stable. It's actually not that slow. Looks like we've got a bug here with our cell lookup, though. But I'm not sure why. So probably can't look at these values. So it looks like we've got a bug here for lookups where our clamped is not doing the right thing. Let me just take a look. I mean, that looks like it should be fairly protected. So I'm not sure why we're getting that bug, but it could be also that maybe the TYTX values could be bogus as well. Not 100% sure about that either way. Oops. Yeah, so we're going to need to, let's go to brief Q&A because I think that's it for today. We'll pick that up tomorrow at that point. There we go. Forgot what the heck to type. The UI is drawn at Z levels less than -999. So to disable the lighting, just compare the Z to -999. Can you quickly re-enable it? So you just mean you want me to do in here, you're talking about this? Like you want a thing inside the, you want a thing inside here that's like, where's our world position? I don't actually know where our world position is. World P. So you're saying world P, you want this? I'm not sure if that's what you mean. Is this what we're talking about? Which is fine, although I'm not sure I would want to actually do it that way. In the long run, right? I mean, I'm gonna want to actually turn it off for reals. So that's not something I would want to leave in there, but sure. Why not? I think mostly, yeah. I mean, if we look at the light propagation work here, so I mean, the thing that I would want to know, you know, if we were going to play around with this, I'd want to know which one of these two passes is our actual hotspot now. So if we take a look at this timed function, what I'd actually want to do here is split this in half. So in our, I probably want to break it into 2 blocks. Timed block, like in here. So I would probably want to do like, you know, oops, timed block, or you know what? I don't even really need to do that. I guess I think I can just do this. Well, so this is hard because we'd have to actually start it each time, but all right, so maybe this. This is a little janky, but we'll see. Hides previous declaration. Oh, come on. All right. I don't care that it hides the previous declaration is the thing. Like, I don't care about that even a little bit. But yeah. Oh, you know what I can do? Here's what I can do. I'll just time full cast. That's what I'll do. So if you want to look at the time, I'm assuming the reason you wanted the profile on is because you just wanted to see where the time is being spent, because obviously we need to know that for later. But so if we look in here, we just so you can kind of see like a little bit of a breakdown here, and you don't know how accurate that really is timing wise. So it's probably not too far off from the truth. So if you take a look here, you can see that a significant amount of time is spent in just the filtering of the maps. So, you know, full cast is definitely the big loser, presumably because of the filters, the sampling step. So I'm guessing, and I could be wrong, but I'm guessing that this disaster here is most of the issue. I don't know for sure, but just assuming that we actually told the optimizer, like, hey, man, don't bother with any of that. Just use, like, one of these things. So that we weren't looking up all that stuff. I'm assuming then it would get a little bit more generous. Or maybe not. Is that really true? That this is not a particularly expensive part of the process? This is going to throw our numbers off a lot, but seems like you can't actually do insertions of those, which makes sense because I guess they change how the numbering scheme goes. But what just happened? So how are we getting an error on that? Why would we not be able to have a timed function inside here? Oh, because we call it too many times. Right. Yeah, all right. No, that's fair. It's just gonna, we're not even gonna have enough room in the debug log to store how many times we call it because we call it so many times. Fair enough. So, all right. Not great. Not great. So I'm not sure how to really get too much information out of that other than to just say, well, we can get rid of the call to it, right? And see how bad that is. So we could just say here, look, the light sample that comes back here is just going to be some other thing. So, you know, it's like something like this. So like, yeah, the light sample is always some stupid light in this case. So if we have the ability to switch between those, like so, we could flip them on and off and see what the optimizer produces for those two cases. So here's what we would get if we're running with a light source just stuffed in there. So without compute voxel or radiance at causing any problems for us, in theory. And actually, the difference isn't that much. So that's pretty interesting to me because that actually means, so it's just the raycast cost and the sampling the light at the result is not a big deal, which is interesting to me. I mean, if that's the case, that's actually great because the raycast is a lot easier for us to fix. So turning it on, I mean, it does get slower, but not nearly as slower as I would have thought. So I guess that's really kind of encouraging because it means the hardest thing to speed up, which is this, is actually, and we can do it wide, so that'll speed it up a little. But it means that the actual raycast is the thing that's causing the most pain. And that's good, actually, because that's the thing we probably have the most control over to a certain extent. Just in terms of, like, what we can speed up and what we can't. That's what I'd say about that. So, yeah, I guess that leaves us in a pretty good place. I think you mentioned before that you don't like regular expressions. Can you elaborate on why? Yeah, it's pretty simple. I just think that the syntax is so cryptic and weird that it just doesn't make a lot of sense to me why you would standardize on this. Like, the amount of time it takes me to type in something I want to find in my text is not a huge deal. So why not just give me a more straightforward, easy to read thing that I can do? Like, why do I want to remember what, like, brackets dot slash 3 star bracket star plus means or something, right? When you could have just made it an actual reasonable language to read, because the number of times that I type these in is pretty low, and the number of times I have to sit there going, oh, wait, so what's the right way to say that I do want a space, but I don't want a this, you know, just like, it's just bad design, in my opinion. You know, it's just bad design. I don't think there's anything wrong with making a subset of the parsable things that we know we can accelerate. So that part's okay. But just the syntax is just garbage, in my opinion, and it should be replaced. If we have a probe near a wall and that probe is updated with a color sampled at the wall, the next frame the wall might be brighter due to the new probe color. Couldn't this spiral up to a very bright probe? How to prevent this? So the idea is no. Absent bugs like the one that we had there, the idea is that no, it wouldn't. And the reason for that is because the probe is measuring how much light flow there is through that probe. And in theory, when it samples a wall, it can only get some convex combination of light flowing through that from that wall, right? And so at no point should we ever be able to actually produce more flowing light than we ever introduced into the system to begin with, right? The whole point is if we just measure the light flow, how much light is flowing through that area, it shouldn't ever be able to be more than the maximum amount of light that we ever have flowing that we inject, right? So what we want to avoid is accumulating light, but we try not to do that by just always measuring the amount of light flowing, right? So we try not to store up light in a way that can accumulate over time. Instead, we try to just blend towards a value that is how much light is flowing now. And so hopefully, no, we don't have the situation that you're talking about. That's the idea anyway. It's puss food time. The puss coming. She's surveying the landscape. You can't see her, but she's looking around. She's decided the bull is safe to approach. And now the food crunching will begin. All right, I think we're all good here. Actually, I guess I can leave that in. That was not really causing a problem, I guess. Also, what's our ray bundle count? Like, if we change the ray bundle count down, how many sphere sample directions are there? How much does it cost to do one? Just curious. So just doing one raycast is actually fairly inexpensive, right? Looks like. And then you really get the runtime dominated by filtering that diffuse map. So that's pretty interesting. We need to change to actually using the diffuse map in practice, but interesting. It's kind of fun. You end up like, with that slow of an update rate, you end up kind of like dropping light behind you as you go, which is kind of fun. So what is that? Like, what about if it was 4? So the game actually runs not that poorly with, reasonable indirect lighting already. I mean, I'm pretty happy with where this is at, right? I think we're going to be able to tighten this down. I mean, it's looking pretty cool, and honestly, at this point, like, I think we're within striking distance. We have a lot of finishing work to do, but yeah, it's not looking too bad. So I also wonder, can we now turn our bias towards the light source back on? I don't really know that we want this. I'm still not sure if this is a good idea or a bad idea, but I'm just curious. So what's going on here? Okay, we've got a startup situation. I'm not going to end for the day. I want to see what that bug is. So we should, since we can just start the code now, I should be able to run it in debug mode, get whatever the out of bounds error is here, and look at what the problem is. So, you know, those are not great values of ty and tx, you know, if we're going to go ahead and be completely honest about it. So what's the problem here? So we've got all 0 R. So the octahedral offset we're asking for is R, and we're getting back garbage. So what's up with that? I don't actually know how to... Let's provoke this. So here's get octahedral offset, and we're passing 0 in here, right? And so I just want to know, is it because of like the floor function is broken or something? Let's find out what we're getting. So if dir is all zeros, we're saying we get garbage back. Is that correct? I neglected to actually look at the function. Okay, so here we are. Get octahedral offset. I'm going to cold set this to 0, 0, 0 there. So unfortunately, this is still multi-threaded as well, so that's a bit of an issue. So I guess we really just want to set the breakpoint there, and not there. All right, so Dirk came in as 0, 0, 0. Well, it didn't come in as 0, 0. We set it to 0, 0, 0. What's the result? Yep, it's garbage. So what's the UV? The UV is garbage. So it's this octahedral from unit vector that's messed up. So if you pass all zeros to octahedral from unit vector, you get a garbage value out. So let's find out what that is. So here's here is octahedral from unit vector. And somehow if this is all zeros, then you get that. Oh, well, it's because of that. Oh, but actually, wait, yeah, so how do you pass 0, 0, 0 to something? Now that I think about it, that makes perfect sense. That can't be right, because you're not allowed to actually do that. So this one norm, yeah, So I'm not sure how we would avoid that, but presumably what we would want to do is avoid that earlier on, right? Because, yeah, this is not defined for that. And where that's coming from is if you have to sample the light direction, and the light direction is ill-defined, right? So let me just go take a look at that. So if we do a get octahedral offset, and we look at where that's actually happening, so the normals should never be able to do that. So we're really looking at, yeah. So this emission direction here would be the problem, and basically like this right here would be an issue if point on light and ray origin are the same. You know what I'm saying? That would be an issue. And so we need some way of avoiding that actual eventuality. So I guess we would just have to, I don't know what we would do in that case, but that would be our issue. So the approx NAS here that we're doing, you know, I don't know, like where we do this select, and we're selecting from the original result value, it's almost like this thing needs to be filled with real values at that point, right? You don't want NAS, you want like a prox, normal or, you know, up or something, right? So you want that, I think. So in here, you basically say like, initialize this to the up vector or something, right? And that way, if you try to normalize something and fail, you hand it the up vector back instead of nothing, right? So presumably we want something like that. Now, of course, I don't actually know where this particular one's coming from, so I'm going to try and find out, right? What are we looking at here? Emission direction. So how are we getting when... Let me just take a look. Well, that's weird. So the emission direction here, though, is not zeros. Did I forget to get rid of the 0 or something? No. So how is that producing an all 0 value there? Do we actually have a surface normal that's 0? So how are we getting a surface normal that's 0? What's up with that? So the sample n that we're passing down here is wrong. It's probe sample n, right? So we said we hit a surface, but we didn't fill in any normal for that surface, apparently, right? Which is total garbage. So how did that happen? Because that's like never supposed to happen. And I'm not sure what we did there, but we did something wrong. So our raycast here is busted at least a little bit. Because where we actually do our computation here, it looks like the hit normal for one of the lanes that said it actually got hit did not produce a valid normal, right? So there's something busted there. I'm not sure what, but that's what that is. In the case where we hit something emissive, it should still give us a normal, right? Like we should never actually have that case. And yeah. It looks like we must have a bug in this code somewhere in order to produce that. Because we're generating this normal, so it should never actually be the case that one of these things that did hit. So basically this hit normal, this code should always produce a valid normal if you ever had a valid hit. And it's not doing that, so this code is probably garbage. So if the X mask, Y mask, Z mask are not properly computed, so this is an X less than Y and X less than Z. This is a Y less than X, Y less than Z. So, I mean, I guess part of the problem is if this hit directly, no one would trigger. Right? So probably this sort of thing has to be like a less than or equal to for somebody. Right? Trying to think of how that would work, but let's suppose that all these values are 0. If all these values are 0, then none of this comes back right. You know what I mean? It's like, so when values are equal, you have a problem. If you change them all to great, so if you have a case where, yeah, I mean, I guess what I'd say is what you probably want is something like this. If X is less than or equal to Y, X is less than or equal to Z. So in the case where all three are equal, if not all three things are equal, then one of these things would work normally, right? Let No, that's not true. So how about that? So if all three things are equal, X will fire. So it will get set and Y will not, right? Because this one won't work. If just two of them are equal, then there's either X and Y are equal, X and Z, or Y and Z. If X and Y are equal, then this one will trigger and this one won't, right? If X, and obviously this one won't. If X and Z are equal, then this one will trigger and this one won't, right? And if Y and Z are equal, then well, I guess I said that a little bit wrong. So if X and Y are equal, but Z is not, then this should fail and this should succeed. I'm not thinking about this correctly. So in the case where X and Y are equal, but Z is not, then you would get a situation here, I guess, which would develop. So, okay, so just bear with me for a second. I want to see if this corrects that particular problem. Yeah. So I do think I want to put in, I probably shouldn't start on this today, but so I'm not sure about that one there, right? Like, I'm not sure that really did the trick, but basically what we need to do is make sure that this always produces a normal that has only one value, right? No matter what. Yeah. So, okay, so this is the version that biases towards the lights as well. So the first direction is always probing the light source. And, you know, I'm not sure, again, like that this really makes a difference. So we may just take that out. Looking at it here, if I go back to the full cast routine, the only difference, right, is you put this guy up here, or you don't, right? So if you look at the difference between the two, they're pretty minimal. So, I mean, it could be busted, right? As well. So I don't actually know, but I'm tempted to say we don't care about that very much. So we may just not need to do that. We'll see. But yeah, I don't know that it matters much, right? Actually, I guess if it doesn't matter, I'd probably leave it this way. So you just sample the ray bundle, and then in here you would just, you know, get rid of this. So we just do something like that. And there we go. So I'll probably just leave it like that for now because it doesn't seem like that's necessary. And the way that the lighting works, I think it seems like we'll be all right. So we'll see. I think that biasing might not be necessary. All right, so I think we're all right. So I'm going to go ahead and close it down. I've got a question here. How do you share memory across functions in a shared library? I know the user could allocate memory and pass that to the library, but I was wondering how to have the library allocate memory for internal use without the library user having to know anything about it. I guess what I would say is I generally don't think that's a good idea. But that's beside the point. If it's just you're asking how do I do it, you should be able to do what you said. So when you say I tried using a global that gets initialized in the DLL main with virtual alloc, but later when I call a function, the library exports the global is 0, that sounds like you have a different problem, because you should be able to do that, right? That should actually work. So you probably have a different problem happening, because you should be allowed to, in DLL main, do a virtual alloc and store that and then use it. So something else is probably happening, but you should be able to do what you're talking about. All right, let's go ahead and wrap it up. Thank you, everyone, for joining me for an episode of Handmade Hero. It's been a pleasure coding with you, as always. I'm pretty excited with how that lighting is turning out. I think we've only got a little bit more of a push before we've got a really snazzy lighting system looking there. And this one, unlike the first one we wrote, this one works for per pixel lighting everywhere in the whole game at all times, too, which is pretty great. So I'm really excited to kind of push forward on that a little bit more. As usual, if you want to follow along with the series at home, you can always pre-order the game on handmadehero.org, and it comes with a source code so you can do your own experiments with it. Maybe you can figure out some ways to optimize our lighting before I get to it tomorrow. But I will be back here tomorrow to start looking at exactly that. So hope to see you back here for that. Until then, have fun programming, everyone, and I'll see you on the internet. Take it easy, everybody.